The tunnel-following NMPC scheme is a natural extension of the path-following scheme where the n effector of a robot manipulator is allowed to deviate from a position reference up to a distance ρ, heavily penalizing any excursion beyond ρ in the objective function of the underlying optimal control problem. Such additional freedom can be exploited to obtain optimal motions. This scheme was introduced for a position tunnel by van Decré in 2019. The first contribution of this work is an extension of the tunnel-following scheme to include freedom not only in the position of the n effector but also in its orientation. The orientation tunnel, as we call it, is built based on some error angles theta, phi, and psi that describe the distance between the rotation matrices representing the orientation reference and the orientation of the n effector. The constraints that define the position and orientation tunnels are defined as a squared L2 norm of the corresponding error measure, which must be lower than the tolerance ρ squared. This constraint is relaxed by means of a slack variable. These constraints are part of the nonlinear program of the tunnel-following scheme, which have functions in the objective and constraints with a special structure called convex over nonlinear. The convexity in the outer function of convex over nonlinear functions can be exploited by the sequential convex quadratic programming method, which creates an approximation of the Hessian of the Lagrangian of the NLP and replaces the exact Hessian in the sequential quadratic programming method. However, the implementation of the SCQP method requires additional steps like identifying convex over nonlinear constraints and constructing the Hessian approximation, which are steps that a robotics engineer will hope to find abstracted away in a framework to reduce the engineering time needed to prepare and solve this optimal control problem. The second contribution of this work is a novel operator called the line operator that uses symbolic linearization to discard the information of second-order derivatives of symbolic expressions. This way, the original NLP of the tunnel-following scheme can be converted into an alternative NLP with little effort by applying the line operator to the nonlinear part in the objective and constraints, leading to a transparent and easy implementation of the SCQP method. Similarly, the line operator can be applied to all the constraints and the nonlinear part in the objective to implement the generalized Gauss-Newton method in a few steps. We demonstrate the synergy and effectiveness of our two contributions by simulating a tunnel-following task where a 7 degrees of freedom robot follows a lemniscate-shaped path. Our approach, here labeled as SCQP, is compared against the interior point solver IPOPT and the original position tunnel following scheme by van Decré. As you can see from the error plots, the position tunnel constraint is relaxed by means of the slack variable L to preserve the possibility of finding a feasible solution. Also, the orientation tunnel constraint is satisfied along the whole trajectory without exceeding the tolerance ρ sub O, which is not the case for the original position tunnel implementation by van Decré. Regarding the solution time of the evaluated methods, including GGN and the SQP method with the exact Hessian, we can see that despite having additional information from the convex over nonlinear constraints, the addition of the orientation tunnel constraint with the SCQP method has little effect on computation time with respect to GGN and the original position tunnel scheme. Even though the task executed with a 7 degrees of freedom robot is kinematically redundant, our orientation error extension allows to naturally exploit the remaining freedom to obey orientation constraints with no adverse effect on position error and little effect on computation time.